right, this is the third part of 1.2, and we broke it up into 3 parts so it didn't seem quite so overwhelming. In this part, we're going to be defining domains of rational and radical expressions. Rational expressions are when you have the variable in the denominator. A radical expression is when you have the variable underneath the radical. So I'm going to show you each of these, but there's some things that are true. When I ask to find the domain, that's telling me the domain is how many values, what possible values can I use for x. All right? So it's kind of weird when we say we're finding the domain. What we're really doing is we're finding what the domain cannot be. Okay? What can the number not be in the denominator? Okay, so for this, what number cannot be in the denominator of a fraction? Well, we know that the denominator cannot equal 0, ever. Okay, you can never have 0 in the denominator, ever, ever, ever. I don't care if you take calculus, you cannot have 0 in the denominator. Okay, so then what we do is we find out what number it can't be to find our domain. So I'm going to take wherever that variable in the denominator is, and I'm going to set it equal to 0. Or set it actually, I say set it not equal to 0 because I think that makes more sense. Okay, set the denominator not equal to 0 because we're trying to find what it cannot be because it can't be 0. So we have x plus 6 cannot equal 0. Subtract 6 from both sides. I'm doing these real baby steps here. And x cannot equal negative 6. So if I put that on a number line, and I've got 0 for reference and negative 6, remember, we always use open circles when something's not included. And so if I do my graph here, this is negative infinity to positive infinity. And I know that I'm going to have an open circle on x because it cannot equal 6. But it can be everything else. So this is going to go out here, and it's going to go out here. Right? So when we do our interval notation, we have 2 different parts. We can go from negative infinity, and remember negatives have parentheses, and we have values all the way up to negative 6, but not including 6. And then it picks up at negative 6, not including it, and goes to positive infinity. And remember that the brackets mean that 6 is not included. Okay? So that's the domain listed, written like an equation form. This is the domain in a graph form. And this is a domain in interval notation form. And we're figuring out what cannot be, because it can be everything else. Okay, let's try this next one. I take whatever's in the denominator. You don't even have to pay any attention to the numerator. It's all about not having 0 in the denominator. And I'm going to set that not equal to 0. So I have 3x minus 15 does not equal 0. I'm going to add 15 to both sides. So I have 3x does not equal 15. Divide both sides by 3. And x cannot equal 5. I should probably box those when I do this. Cannot equal 5. So if I do my number line, and remember this is negative infinity, this is positive infinity, I have a 0 here and a 5 here. I know it can be everything, but it can't be 5. So the 5 is going to be a big open circle, and we're going to have values all the way to the ends on both sides. So when we do our interval notation, it starts out pointing to negative infinity and goes up to 5. Infinities always get parentheses. The 5 gets parentheses because it's not included. And then we start at 5 but not included, and then go out to positive infinity. And that's your interval notation for that. All right, so the first type of domain we find is for a rational expression. These are rationals, which means you've got an x in the denominator. You set the denominator equal to 0, and then that will tell you what x cannot be. All right. Okay, the other kind of finding domains is what cannot be under a radical. Right? Now this is a little bit different. You can have 0 under the radical because the square root of 0 is 0. But what you can't have under the radical is negative numbers. There can be no negative numbers under the radical. So that means that your radicand, the thing underneath the radical, has to be greater than or equal to 0. Okay? So for the denominator, whatever's under the denominator cannot equal 0, but whatever's under the radical has to be greater than or equal to 0 so that it's positive. It can't be negative. All right, so I'm going to take what's under the radical, x plus 5. I'm going to make it greater than or equal to 0 because we can't be negative. Subtract 5 from both sides, and x is greater than or equal to negative 5. Okay, this can be negative. It's just when you plug it in, you can't get a negative as a result underneath. Then if I graph that, I've got, let's go negative 5 and 0. And it's equal to, so it's going to circle on the negative 5 and points out towards positive infinity. So then my interval notation starts at -5 with a bracket because I'm including it, and then it goes out to positive infinity with the parentheses for my interval notation. Okay, we're going to do one more under the radicand. This is a really short lesson on this one. Okay. Again, this is a radical, so the radicand, whatever's under here, has to be greater than or equal to 0 because it has to be positive. We subtract 24 from both sides. Okay, negative 6x is greater than or equal to negative 24. I'm going to divide by negative 6. When we divide by a negative number, we flip the inequality, and that's my domain for my radical in equation form. I'm going to graph it. So I have 0 and 4. My circle's on the 4, and it's closed because I have a line in it. It's a closed circle, and it's pointing to the left. So this one's going out this way. All right, this is negative infinity. This is positive infinity. And then your graph will always dictate your interval notation. So we just go from left to right, starting at negative infinity. It goes all the way up to 4. And since I'm including it, I'm going to put a bracket. And that's all we have to do with finding domains for radicals and rational numbers.